Hello class, you are most welcome for today's lessons. I'm Mr. Chan Kaunda that will be taking you through an exciting topics in physics. And we're going to look at the topics in Senior 3, that is refractions, dispersions, and colors. But for today, we are going to pick and look at refractions. I want to start by asking, have you ever seen a rainbow in the sky? Or notice a pencil looks when it is in a glass of water? This happens because of bending of light. When light travels from one place to another, like from air to water, it doesn't move in straight line. Instead, it bends. So when you see the pencil in water, the light bends as it moves from water to air, making the pencils appear to be in different positions. Everything we see around us, from rainbow to our object look under water. Sometimes we will look at the object being raised up beneath the water. This happens because of refractions. So when light travels from one medium, like air or glass, to another medium, like water or glass, it bends. This bending of light is called refraction. So refraction happens because light moves at different speeds in a different materials. Yes, let's start our topics by asking ourselves what refractions of light is. So refractions is a change in the directions or bending of light rays when it travels from one medium to another of different optical densities. When I said optical densities, this refers to how much a material slows down light as it passes through. The denser the medium, the more it slows light. Light travels faster or bends less in a vacuum and slower or bends more in a material like air or water or glass. Important terms used in refractions of light. Let's consider the two mediums. Medium 1, and in this case, let's say it is air, and medium 2, let's say it is a glass. Then when a ray of light travels from a less dense medium, which is air, or medium 1, to a more dense medium, which is a glass, then the refracted rays will be refracted towards the north. Then you shall see that the AO is the incident ray, the OB is the refracted rays, and the lines between the medium 1 or the line that separates medium 1 and medium 2 is the boundary lines. Then the line that cuts the boundary line perpendicular at 90 degrees. This line is what we call the normal. And when the refractions happened, we see that the angle of incident I is greater than the angle of refractions R. Again, let's look at the terms used in refraction of light. If you are to consider this ray diagram, shall see that the boundary lines, this is the line that separates the two materials or media where refractions happens. The incident rays AO, this is the ray of light that hits or falls on the boundary from the first medium. Then refracted rays OB, this is the ray of light that leaves the boundary into the second medium. It is in the opposite side of the incident ray. Then the normal NM. This is the lines or an imaginary lines that is at 90 degrees to the boundary. It helps to show that light hitting the boundary at 90 degrees or normally doesn't bend or change directions. And the incidence angles I, this is the angles between the incident ray and the normals. Meanwhile, the refracted angles R, this is the angles between the refractive ray and the normals. And we have to note that when light moves from a denser medium like water or glass to a less dense medium like air, it bends away from the normal. Meanwhile, if the light moves from less dense medium like air to a denser medium like a water or glass, it bends towards the normal. So when you can see that the angles of incident, it is greater than the angle of refractions of light, because here the ray of light moves from the less dense medium to a denser medium where the refracted rays bends towards the normal. Laws of refractions. Let's consider this ray diagram. In the ray diagram, we shall see that the incident ray, the normal, and the refracted rays, they are having a common point, which will help us to come up with the first law of refractions. And it states that the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same planes. This means that they are all on the same flat surface when light bends. Meanwhile, the second law states that the ratio of the sine of the angle of incidence to the sine of the angle of refractions for a given pair of the medium is a constant. So when you have the sine of the angle of incidence and equate it to the sine of the angle of refractions, should give you a constant. And that constant is what we call the refractive index of the material. The second law of refractions is referred to as the Snell's law. And this has been derived by a Dutch mathematician, Wilbert Snell, in 1621. The constant in the second law is called the refractive index, which is denoted by n. Sometimes we also represent that one with the lambda, where the refractive index n is equal to the sine of the angle I over the sine of the angle R. And for the glass, its refractive index is 1.5. So now what do we mean by refractive index? So this is the ratio of sine of the angle of incidence to the sine of the angle of refractions for a ray of light moving from medium 1 to another of different optical densities. It also shows that how light bends or refracts when it enters a new medium. For example, for a ray of light moving from air to glass, then with the ratio will be the ratio of the sine of the angle to incidence in air to the sine of the angle of refractions in glass. Alternatively, we can define refractive index as the ratio of the speed of light in medium 1 to the speed of light in medium 2. Hence, our refractive index n is the speed of light in medium 1 to the speed of light in medium 2. For ways you can express it in terms of the refractive index n is equals to the V1, which is the speed of light in medium 1, over V2, which is the speed of light in medium 2. Having already seen and looked at the refractive index, where we said this is the ratio of the sine of the angle of incidence to the sine of the angle of refractions. Now we want to look at how can we determine the refractive index of a glass block. For us to determine the refractive index of the glass block, materials that we need to use are the glass block. We need to have a soft board. We need to have a geometry set. Sometimes you call it a mathematical set. We need to have paints, and here we can have 4 optical paints. We need to have 4 drawing paints, and lastly we need to have a plain white sheet of paper. So you are going to fix a white sheet of paper on a soft board using the drawing paints. So if this is our sheet of paper, here we can fix the paints there. We can fix another drawing paints here. We can fix another drawing paints at this edge, and lastly we can fix that paint there. After fixing the paint, you bring the glass block and place it in the middle of the white sheet of paper. So you come and place this glass block in the middle of the white sheet of paper. After placing the glass block, then you trace its outline using maybe your pencils and level it. We can level it as A. We can level this edge as B. We can level it as C. Then we can level it as D. Then after leveling it, you remove the glass block and draw a normal. You can draw this normal, saying that maybe at the point N, as we already said there, mean that the normal line that you are going to draw here, it should come and meet the side of the glass block AB perpendicularly. This one should meet perpendicularly. Then you, using now your protractor, you come and measure the angle from the normal, saying this angle I. You measure maybe angle I to be equals to 20 degrees from the normal. Then you draw a line on that angle, and this line that you're drawing will act as the incident ray. Then on that line, you bring 2 paints. You come and fix it, and here we are calling this paint to be the paint P1, and also we are calling the paint to be the paint P2. So you come and fix this paint P1 and P2 onto the line that you have drawn. Then after fixing the paint, you replace the glass block back onto its outline. So you come and bring the glass block, you put it back along this trace outline that you have done earlier. Then coming into the side DC of your glass block, you look through the glass block and fixed again 2 paints, and here now we are going to call those paints, we shall call it to be the paint P3 and paint P4. So the paint P3 and paint P4 should be fixed in line with the image of the paint P1 and paint P2. After fixing those paint P3 and paint P4, then now you remove the glass block together with the paint P3 and paint P4. So you remove this glass block together with the paint P3 and paint P4. Then after removing, you draw a line passing through the point of the plane P3 and plane P4 to meet the side of the glass block DC at point M. And this line that you're drawn, we call it to be the emergent line or the emergent ray. Then you join now from the point where the line meets the side of the glass block DC at point M. Now you join the line from point M to point end. And this line joining the point M to point end is the refracted ray, where the angle between that line and the normal, it is what we call the refracted angle. Then using now the protractor, you come and measure this angle R. You measure the angle R now here. Then after measuring the angle R, you come and repeat the experiment for different values of I, saying maybe the I to be equals to 20 degree, 30 degree, 40 degree, 50 degree, and maybe 60 degree. Then after varying the angle I, and also you have measured the angle R, then now you tabulate the results, including the sine of the angle of incident and also sine of angle of refractions. Yes, now on our table of values, what we need to do is that we have already started with angle I to be 20, then we have gone to 30, we have gone to 40, we have gone to 50. And this I is the angle of incidence in degree. Then also you have measured your angle of R, saying maybe that you have measured this angle I and you have recorded them down here. So now you come in the column for sine of I. Using our calculators, which is set in dec, which is degree, you come and press sine of I, and in this our I is 20, you press sine of 20, you come and record the values here. You press sine of 30, you come and record the value here. You press sine of 40, you come and record the values here. You press sine of 50, you come and record the values here. But when you're recording the values, it must be in the 3 decimal place. If you are recording it in sine, then it must be the 3 decimal place. The same thing that you have done for I, sine of I, must also be done for sine of R. So saying maybe that if this is, assuming it is 14 degree, so still you come and press sine of 14 degree, you come and record it in 4 dp. Then maybe if this is 19 degree, you come and press sine of 19, you come and record. But all this recording must be to 3 decimal place, the 3 decimal place. That is how you'll fill your tables of values. Having already tabulated our results in the table of values, then we need to plot a graph. And a graph that we should plot a graph of sine of the angle of incident against sine of angle of refractions, where we said sine of I against sine of R. Now in that graph, we shall have this sine of I in the vertical axis against sine of R in the horizontal axis. So now, because now you'll be having those values in our table of values, then you are going to have, when you plotted the graph, you will have a straight line graph passing through the origin here. So this straight line graph, when you are to get the slope of that graph, So if you are to get the slope of that graph that you are going to plot, then the slope of that graph, if you have to extract a right angle triangle, then now this one become the change in sine of the angle of incident. This is sine of I against the change in sine of R. Against the change in sine of R. So this slope of this graph is the same as our refractive index. And since we are considering the refractive index for the glass block, which means this refractive index should be equals to 1.5. Should be equals to 1.5. And now because this the sign of the angle of incidence, they don't have the SI unit. Therefore, our refractive index also will not have the SI unit. Thank you so much for attending the lessons. I still remained Mr. Ochan Kenneth Kaunda, your physics teacher. See you again in the next lessons. Thanks.